attention to covalently bonded compounds is because you can draw a complicated Lewis dot structure of any compound that you want. Okay, for an example, let's just start out with one called CF4. Now what I'm going to do is I'm going to put a list on the right hand side of the board, and maybe you want to make one too in your notes. I don't know what you want to do. And then we'll use that list, steps 1 through 6, to talk about these Lewis dot structures as we progress through them. All right. Now this is Freon here. It's a type of Freon. There's numerous types of Freon. And we want to get a picture of it. That's the whole point of this chapter, is bonding, is a picture, and that's called a Lewis dot structure. You see, whenever things react, the reason you want to get a picture is in organic chemistry and so forth, you have to know what molecules look like, all right? Because whenever things react, they react in a very specific way along a potential surface. So, if you were a betting person, okay, and we've already drew up ammonia here, and I've not told you how to do this. If ammonia was going to react, where do you think it would react at? Would it react on the hydrogens most likely, or would it react on the nitrogen? Nitrogen, why? That's where the electrons are. Take a look at this here. Here comes this thing flying in. That ain't worth nothing. But here comes a molecule flying in. That's good news. All right, and that nitrogen's classic for doing that, right? It's what's called a nitrogenous base. So if you look at any type of painkiller, morphine, Dilaudid, any of those opiate derivatives, they all got that big nitrogen boy sitting right there. And that's useful when it comes to the way that it's used for pain management, chemical reactivity, and the such. So you have to know what the thing looks like, because, you know, sometimes molecules have sites that things just naturally will fall into, and sometimes they have sites where they don't naturally fall into. All right, so the point from here on out is to find the sites, to find what it looks like, the shape of the compound. The first one is count the number of valence electrons, and we're going to call this right here Joe's rules, right? That's official. You're not going to find that anywhere else, right? So Joule's rule said, let's just go ahead and count the number of valence electrons. How many do we have? Well, here we've got a carbon, a fluorine, a fluorine, a fluorine, a fluorine, and that's it. So how many valence electrons does carbon have? 4. Wonderful. How about fluorine? 7. So how many is that total? 28 plus 4 is 32 valence electrons. Is there anybody confused about how you would do step 1 in getting the picture of the compound? All right. Step 2 is you're going to pick a central atom. All right. And that is done, it's the one that is always the lowest electronegative atom, and it cannot be hydrogen. All right. Hydrogen cannot go in the middle of a compound. Now I have seen it. It's called an Iliad, Y-L-I-D-E, but I've only seen it once in my life. All right. And it's a very short-lived type of an intermediate state. So in freshman chemistry, you ain't never going to have hydrogen sitting in the middle of a molecule. All right? Even if it's the one that's the lowest electronegativity, it will not be hydrogen. So let's look, see, carbon, fluorine, which one's the lowest? We now have ourselves a central atom. All right? Now, the third thing that we've got is we now have to build a skeleton. Build a skeleton. Okay. So, let's put a fluorine here, a fluorine here, fluorine here, fluorine here. Now, for right now, here's what you need to remember. This book does not go into a topic called VSEPR with any rigor at all. It mentions the term, and it goes on for a couple of paragraphs. And what VSEPR stands for is valence shell electron pair repulsion theory. All right? And that is something you will learn in the next chemistry in depth. All right? And basically what VSEPR is it just shows you how everything is the equally spaced as possible. All right? So next semester, this picture will turn into something that's called tetrahedral with 109.5 bond degree angles and all this drama. All right? But for right now, they're just kind of sitting there. The fourth thing you're going to do is just going to be the terminal atoms must obey the octet. Now I want to underline the word must, because that means there's not an exception here of where the atom will not obey the octet. Kind of. I'll get there in a minute. All right, but must be like the noble gas. Must be like the noble gas, right? All right, so now that's 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. How many electrons are on the board? 32. We are officially done. Let's see if it makes sense. Would you expect, using your chemical intuition, that the most electrons would be located on fluorine or carbon? Where are they at? Fluorine. Okay. There's a couple more rules. The fifth rule says, if we have extra electrons, which, see, we don't here, but naturally, as you can imagine, this is a very simple Simon example to get your feet wet, right? We dump those, DUMP, dump those on the central atom. Now, here's what that means. And don't nobody write this down, because then you're going to be confused. That means if this number was a 33, where would we put the extra electron? Right there. All right. Now that number was not a 33. That number was a 32, so we didn't have to go through that rule. Now, sixth rule says, the central atom does not have to obey the octet. But if it can, it will. All right? And you'll just have to stay tuned for me to explain that one to you. The central atom does not necessarily have to have 8 electrons around it. How many electrons does this joker have around it, central atom?
2.
No, the central atom.
4.
No. 8. 2, 4, 6, 8. Remember, every time you see a line, that's how many electrons? 2. One from the fluorine and one from the carbon. So around that carbon, how many electrons does it think it's got around it? 8.